Hello, my name is Alexander Fedorov. I am a project lead in the Visualize team, and today I am glad to talk about the last achievements in the Visualize SDK. But at first, a few words for what Visualize SDK is. Visualize SDK is a common-purpose rendering engine, which means that through this SDK can be visualized different kinds of the data. It can be 2D models like massive maps. It can be different 3D models from architecture or engineering world. Also, it can be more specific data like massive meshing models from finite element packages or huge point cloud data. Here also it is need to mention that if we will speak about an engineering graphics nowadays, rendering engine should provide quite wide range of additional functionality other than just a visualization. It's selection, sectioning, collision detection. And Visualize SDK has all such abilities. Some of them will be mentioned today in the context of the new features and improvements which will be discussed. So let's start from one of the main new features, which was many times asked by our customers: shadows. And here I want to introduce you my colleague, Andrew Markovich.
Thank you, Alex. Really, let's speak about shadows. Since modern graphic rendering tasks require more and more realistic representation, like for example realistic viewing of buildings, rooms and civil engineering objects, and modern graphics processing units give us ability to perform this realistic rendering quite fast, we added support for some popular visual effects in our graphics engine. One of these effects is shadows. ODA Graphics Engine supports shadows on all platforms, including desktop, mobile, and WebGL. For all of these platforms, we have stable rendering performance, since each light source shadow map requires only single simplified graphic scene rendering for preparation, and usage of shadow maps during rendering doesn't visually influence onto entire scene rendering performance. In ODA Graphics Engine, we can simply modify any light source properties and shadow parameters, enable or disable lighting, move light sources, or graphic scene objects. During graphic scene modification, all dependent shadow maps will be dynamically recomputed, and we can see final result with shadows immediately. Of course, rendering performance depends from graphic scene complexity, but recomputation of shadow maps done with simplified geometry details, so them doesn't seriously influence on the entire rendering performance. ODA rendering engine supports three kinds of lights: distant light, which represented as single lighting vector; spotlights, which looks like projector inside scene; and point lights, which is represented as points inside scene. And this kind of light source emit lighting in all directions. Point lights are most complex light type for shadows computation. Shadows detalization and quality depends from shadow map size. Also, we support objects transparency during shadows calculation, which give ability to increase final graphics level of details. Shadow maps work well with semi-transparent graphics too. Additionally, to avoid shadow sharp corners and provide more smooth and realistic shadow rendering, we apply blur effect, so final shadows look soft, like this is seen in a real world. ODA Graphics Engine supports any number of light sources with enabled shadows. Everything depends only from graphics scene complexity and graphics processing unit capabilities. But I should add that firstly, quality of final rendering depends from diligence of designer, who is create graphics and place light sources in right places with correct settings for creation of good visual effect. And only secondarily, final rendering quality depends from capabilities of your computer. As in many modern CAD viewing applications, ODA Graphics Engine supports ground shadows. This is a combination of realistic geometry shadow computation and transparent plane onto which is computed shadows drawn. This is popular effects which is provided by ODA Visualize using few options. On current slide pictures we can see how this effects looks on the different kinds of models, including mechanical model, building and bridge. Another popular effect which is intended to increase rendering realism is screen space ambient occlusion. Ambient occlusion is rendering technique which gives ability to add effect of global illumination inside your rendering scene. It is adds some additional shading inside geometry corners, so final result looks more physically correct since light rays re-emitted more times inside corners and final rendering intensity becomes less. Full ambient occlusion implementation requires ray tracing engine. Screen space ambient occlusion represents approximation of ambient occlusion technique. As we can see on pictures, screen space ambient occlusion effect adds small shading around geometry details. For entire scene, these effects may be not so visible like shadows, for example, but it is at additional graphic scene realism, since it is approximate real physical nature of light. Drawings may be drawn in different coordinate spaces, units and dimensions, so default screen space ambient occlusion effect settings may not fit for all of them. For example, focus property defines area in which screen space ambient occlusion effect will produce sampling. This property defines hemisphere in a world coordinate space of drawing, in which screen space ambient occlusion effect will find nearest surface intersections. Larger sampling area will cause a larger area of screen space ambient occlusion effect application. As a result, we can see more effect from screen space ambient occlusion technique. Screen space ambient occlusion is advanced rendering technique, and as for shadows rendering, to reach best result, it may require some additional configuration for specific final application. To configure screen space ambient occlusion, you may use a set of parameters like focus, effect power, number of sampling loops, and amount of blur. Screen space ambient occlusion hasn't limits to use it in any kind of application, viewer, editor, exporter. It doesn't depend from ODA product and file format, and it is supported on all platforms, including desktop, mobile, and web. Simply enable and configure it and use freely in your already exist or new application. Okay, let's go back to Alex.
Thanks, Andrew. Last year we presented the anti-aliasing approach, which helped to solve aliasing problem with linear objects like lines, circles, arcs. But the same problem can occur for the 3D geometry, which is represented by triangles, as it is shown on this demo. Here you can see the distortion artifacts at the boundaries of the triangles. For solving this issue, we have implemented the fast approximate anti-aliasing algorithm, FXAA. It is a screen space anti-aliasing algorithm, which represents a single pass pixel shader. The main advantage of this technique is the performance. For this technique, we introduce a few quality settings, which allow to tune the suitable quality level depending on the existing working conditions. One of the typical rendering mode in the engineering application is so-called shaded with edges mode, when over the 3D mesh model, we also render the wireframe representation of the same model, which includes geometry like polylines, circles, and others. The FXAA also works with such wireframe geometry. But one of the FXAA disadvantages is exactly the one-pixel lines. For such lines, the result can look quite blurred. For this case, we have already mentioned special version of the anti-aliasing for the 2D. Using of such technique here allows to receive much better visual results. But the payment for it is the performance. The next topics which we want to discuss today is the collision detection and the progressive mesh. Here I am glad to introduce my colleague Igor Slupko, who will dive deeper into these topics.
Thanks, Alex. Collision detection is a very popular feature in modern engineering applications. For example, it's allowed to investigate the model of building on possible conflict between parts which should not have intersections, like electrical and water equipment. New version of ODA SDK contains extended collision detection functionality. First of all, now it can detect collisions in two different modes. The first mode is intersection mode. With non-zero tolerance, this mode detects collisions if penetration depth is more than specified value. With zero tolerance, this mode detects all intersections and touches. The second mode is clearance mode. This mode detects all intersections and touches, and also it detects as collisions all objects which distance between them is less than specified value. Another new feature of collision detection is option calculate distance. When this option is disabled and we find any appropriate collision between triangles of two objects, we mark these objects as collided and do not process other triangles of these objects. It increases collision detection performance, but makes result less informative. When this option is enabled, we have to check all triangles of two objects, because even if we find collision, another pair of triangles may give greater penetration depth or less clearance value. This mode is more informative because we always can determine kind of collision: penetration, touching, or clearance. This is all about collision detection, so let's move to the next topic. The next topic is devoted to the progressive mesh. And at first, a few words about for what this object needs.
When we render shell data, we have to render all its faces independent of how small this object on the screen. In some cases, we have solid modelers, which can triangulate object with different detalization, and usually it is time-costing operation. But in other cases, we have only a list of faces and have no any detalization mechanism. For such cases, we developed a special object, progressive mesh, that can be built using shell data and can switch its level of details in real time. In new version of ODA SDK, we improve progressive mesh generation performance. It is still a time-costing task, but now it executes much faster. Previous version of progressive mesh supported only manual level of details selection. This means that user had to decide what level of details he would use by himself, and no additional data, like view parameters, were taken into account. In demonstrating sample, progressive mesh level of details can be changed using a slider. However, no other actions, like revectorization, can change level of details no matter of the current zoom factor. This made progressive mesh usage less convenient. New version of progressive mesh supported automated level of details selection. Now, progressive mesh can pick by itself the most appropriate level of details based on view parameters and its own extents. In demonstrating sample, it happens by regenerate command. We provide a few predefined interpolation mechanisms and also a custom interpolation, which can be implemented by user. As I said before, progressive mesh generation becomes faster, but it is still a time-costing operation. However, it is also a single-time operation. When progressive mesh is generated, it can be saved and loaded, and both save and load are pretty fast operations. I also want to note that we save mesh and selected interpolation mechanism, including table representation of user custom interpolation. Now, let's suppose we have a lot of shell objects. For example, original frog model contains about 73,000 4-point faces, so 400 frogs will give us about 60 million triangles. Rendering of this data may be time-consuming. But if we present each frog as progressive mesh and want to see them all, single frog will be small enough on the screen. So, automated level of detail selection will generate about 2,000 triangles for it. That gives less than 1 million triangles in total. So, we can render them faster. Also, we can use regenerate visible command to make only few frogs detailed without recalculation of other frogs.
Now I turn word back to my colleague Alexander Fedorov, and he will continue to present the new features in Visualize SDK.
Thank you, Igor. Selection is one of the most important and used feature in the engineering application. That's why its performance is a key moment. Generally speaking, the selection in Visualize SDK is very fast. But there is one weak point. Big objects with a huge amounts of simple geometries, like big shells or huge point clouds. Using of the spatial tree allows to find the candidate for the selection quickly. But after that, it is need to perform the accurate check. As a result of the presented model, which contains about 3 million of triangles, which distributed between only 7 entities, the simple selection by click will occupy 6 seconds. It is due to the fact that for the shell, the accurate check means that it needs to examine the faces till finding the first which fit the condition. For solving this issue, we have implemented two different approaches, which will be discussed today. The first approach is the GPU selection. The idea is that the scene renders with a special shader in the texture, where each pixel contains an object ID. And as it's possible to see from this demo, the performance dramatically increases, and we are easily in time with mouse moving. But this approach has one important disadvantage. It gives us ability to select only the top object. But in many cases, it is need to select all objects, which, for example, I hit the selection rectangle. For this purpose, we have implemented another approach, using of the local spatial trees. Currently, we have implemented such approach for the unstructured point clouds. The next goal is the shells. For the unstructured point cloud, the idea is the following. If the object contains a big number of points, we will construct for them the internal spatial tree, which will be used for the selection. Let's see what such approach will give us on the example of the presented object, which contains about 20 million of points. Again, we perform a selection by click, and as we can see, it occupies about 8 seconds. Now we will reopen the file with these objects and set the option to use spatial tree for the selection. And as we can see, the selection now are much more fast and occupy less than 2/10 of the second. The next topic which we want to discuss is the VSF file size. The VSF file size can be important in some cases, for example, like transmitting its data to the web. Our SDK use double precision floating point format for the data like vertex coordinates, texture coordinates, normals, and so on. But in many cases, it is possible to downgrade the precision without losing the visual quality. For example, for the normals, it is enough to use single precision floating point format, or in some cases even 2 bytes for all 3 components of the normals vector. And we add a few variants of the compression, like mentioned above, as an option for the procedure of the VSF file saving. And here it is important to note that such compression practically doesn't influence the visual quality of the data which was read from such compressed file. Now let's speak about our activities which is connected to the implementation of the metal rendering engine. During last year, a significant time was spent to the optimization of the process of simultaneous development of the OpenGL ES2 device and metal device. Such work was needed since we want to use in the metal device a significant amount of the features which were implemented during the development of the OpenGL ES2 device. That's why these devices use the same kernel part. But this significantly complicated the simultaneous development of these 2 engines and required additional changes to the kernel part, especially in the area of the shaders. At the same time, we move forward with the new functionality supported now in the metal device: texture support, land weights, as well as initial performance optimization. Now let's start the next block in our presentation, which will be devoted to the extension and examples of the Visualize SDK. And I want to introduce you Vlad Malka, who will drive you through these topics.
Thanks for introducing, Alex. Each year we are trying to expand a set of samples for the Visualize SDK. Last year it is possible to see the growing of the interest to the mobile platforms. Guiding this, we have created an iOS sample last year. Now we are happy to present a sample application for the Android platform.
Android ODA Viewer is native Android application developed using Visualize SDK. Let's look at the main features. Navigation panel contains navigation actions such as pan, orbit, zoom extents, and zoom window. Projection button allows change projection of camera to parallel or perspective. Views panel contains predefined orthographic and isometric views for the camera. Mockups panel allows to create 5 types of mockups objects: rectangle, circle, handle, cloud, and text mockups. It is also possible to save created mockups and then load saved mockups. Also, viewer supports visual styles. For change visual style, need switch on Styles panel and change visual style to one of the panel. For example, to wireframe, hidden line, shaded or other. Tools panel has Collide tool. This tool used for the detection collision between selected entity with other entities. The next feature refers to DWG import parameters. This is low memory import. This parameter allows open DWG files in limited memory mode. In this mode, geometry loading is partially and stop loading when memory exceeds the specified value. After low memory import, created VSF file with partial indexes. It's allow next time fast open VSF file and perform same actions with the file. And the last feature, this is the shadows. Let's open files with different light types. The first file contains distant light. The second file has point light inside house. And the last file has spotlight. That's all about the Android sample, and we are moving to the next topic, Open IFC Viewer.
As with any of our SDKs, the IFC SDK needed an application for testing and demonstrating its capabilities. Using of the Visualize SDK together with the Common Data Access technology allowed to create such application very fast and with minimum resources. We called it Open IFC Viewer. It's a free application which has stable version for Windows and macOS platforms. This application has a rich set of tools. Let's dive deeper and consider the functionality of Open IFC Viewer in more details.
Let's open an IFC file. Navigation actions allow perform different operations with the camera. For example, pan, orbit, free orbit, rotation of view, zoom window and zoom extents. The next features are projection of camera and get snapshot of active view. View panel has several predefined orthographic and isometric views for the camera, and ability to change viewport configuration on single, 2 or 4 viewports with different layout. Possible make viewport is active and perform different operation in this highlighted viewport. Render mode panel allows to change current visual style. For example, on sketchy, hidden line, shaded or another. Mockups panel allow to create different mockups objects. Rectangle, circle, handle, cloud or text mockups. Also possible to save and load saved mockups. Section and panel allow to create cutting plane by X, Y and Z axis with the ability to move, rotate and fill in planes. On collisions panel located Collide tool. This tool for showing collision for selected entity with other entities. And collision detection tool. This tool displays a list of collisions between selected entities. The last is Visual Effects panel. Allow enable FXAA for smoother display and ground shadow for display shadow for the model. Now we are going to the next topic. Publish command for the OpenIFC viewer.
During last time we have received several questions about ability to customize publish command, how to change logo, how to change arrow style, and so on. At the same time we planned to add publish functionality to the OpenIFC viewer, and we wanted to stylize it in accordance to the OpenIFC viewer style. Thus, creating customized publish command according OpenAXE viewer style, we solve two tasks. We add interesting functionality to the application and create additional sample for the users. What's new in the OpenAXE viewer specific publish command? First of all, we added ability to use for the preview generation the same device as an application, including all features, like for example shadows, as in the case of OpenGlass 2 device. Then we have used a new logo, add ability to use images for the arrows in navigation panel, and allow to inherit view parameters from the application for the main preview. Finally, we achieved a significant improvement in the performance. That's all about publish, and we are going to the next topic, PDF export. Let me introduce you my colleague, Evgeny Nikolaenko.
Thanks a lot. Let's speak about the export from Visualize to PDF. During last year, we have added some new functionality here. Let's see the small demo, what abilities we have now. Let's open some DWG file with a few spaces and choose all the spaces for the import. It will give us the presence of a few devices in the Visualize database. And now let's export some data to the PDF. In the export dialog, we are setting some new properties which are available now. Its ability to choose one or few devices for the export, ability to set up background color, and finally, it's possible to define paper size. So let's define all devices for the export and define some custom background color. Now we perform the export, and it's possible to see the resulted PDF file. As you can see, the result is equal to what we have specified.
At the end of the presentation, I want to discuss briefly our future plans. Certainly, this list is not full, but it accurately reflects our near-end plans. The first topic is the block cache and scene graph. Solving of this issue allows us to use block cache option together with scene graph without serious losses in the rendering performance, together with increasing of the visualization performance. Highlighting customization will make our SDK more flexible and allow us to cover a few customer requests. The next topic is a more deep integration of the point cloud and progressive mesh primitives to the rendering engine. It will allow to perform automatic level of detail switching with minimal influence on the performance. The implementing of the subpixel morphological anti-aliasing should solve the mentioned problem of FXAA, when for the one pixel line the result looks too blurred. At the same time, such approach should be significantly faster than mentioned spatial anti-aliasing for the 2D. And a few words about the quite specific topic which is not directly connected with the visualization: export of the Revit sheets to the DWG. Since the Visualize SDK has quite rich import abilities, including Revit, and also has ability to export data to the DWG, using the Visualize for this task looks reasonable. Here I also want to mention that the user's requests are always on the first place, and we can change something in our plans with purpose to add something important to our customers as fast as it will be possible. That's all about Visualize SDK. Many thanks for your attention.